Hello everyone, my name is Andres Mafla and I'm a PhD student from Autonomous University of Barcelona and the Computer Vision Center. In this work we address the task of syntax-based fine-grained image classification and retrieval by employing a multimodal reasoning graph of visual regions and textual information found within an image. Text is a key component towards fully syntax understanding in computer vision models. For example, can you classify the business type in these images without reading any text? The answer is T-businesses. Due to similar visual features of business places in this case, correct classification is nearly impossible by disregarding the syntax, even for humans. This can be generalized to different objects across all tasks in computer vision research. In this work, we employed a graph-based multimodal reasoning module to map complementary regions of visual and textual instances into a common semantic space. We further use these refined features to perform the task of fine-grained classification and retrieval. The final proposed model is composed by 5 modules: global image, local feature, syntax, and positional encoders that interact with the multimodal reasoning module. The global image encoder is comprised by a CNN along a sub-attention mechanism. The local feature encoder is a faster RCNN trained on the visual genome dataset that provides with the features of salient objects, its attributes, and bounding boxes. The syntax encoder uses an OCR to extract text transcriptions present in an image, along with the bounding boxes. The positional encoder receives the bounding boxes of the visual regions and the syntax and are projected into 128-dimensional vectors. The visual and textual encoded features are used as input to the multimodal reasoning module. The multimodal reasoning module uses a graph convolutional neural network to model the complementary semantics between visual and textual regions. Finally, these features are averaged, pooled, and concatenated with the global features to be further classified. In Table 1, we explore the effect of different OCRs: end-to-end, MLT, pyramidal histogram of characters, PHOCs, and a commercial OCR. We explore also different word embeddings such as PHOC and the Fisher vector. In this case, fast text shows a better performance than other word embeddings due to the implicit model semantics as well as word syntax in the form of n-grams that can correct OCR mistakes. As it can be seen in Table 2, our method is robust to perform well in subsets of data that contain and do not contain syntax. And from Table 1 and Table 3, we show that the proposed model outperforms previous state-of-the-art by significant margin in both tasks of fine-grained image classification and query by example image retrieval. In our work, we also show several ablation studies regarding the effect of each module on the final module pipeline. We can see the noticeable effect that is achieved by modeling syntax and visual features in the proposed MMR based on a graph convolutional neural network. We explore several projection methods and fusion strategies. Finally, an average pooling layer and a concatenation of global features and enriched MMR features yielded the best results. The following samples show classification probability scores. We can see that our model is confident whenever syntax is readable, but fails when a wrong transcription is obtained, such as in the previous 2 samples in the first row. The task still contains difficult and ambiguous samples to classify, such as the last image on the second row. There is still room for improvement, especially in cases when visual features are shared among several classes. Finer details in an image provide strong cues, and text is not readable, such as improving an OCR or a scene-based proposal dictionary of text. In the retrieval scenario, and to provide comparative results as previous models, we employ the class probability vector as image features, without any specific metric learning approach. We can observe that the retrieved samples can contain syntax or not, proving the efficacy of our method to combine these 2 different modalities. In our supplementary material, we show more examples. In our work, we also show visualizations of the attention maps and the output features of the MMR module. We can observe that enriched features focus on a barber and the syntax barbershop. A similar effect is achieved within other images as the liquor store and the barrel, the pet shop and the cat, and between tobacco and cigars, showing the semantics of this learned space. And in summary, we show a novel method to exploit the semantics between visual regions along with syntax by using a GCN-based multimodal reasoning module. A new state-of-the-art on classification and retrieval in the context and ring bottle dataset is achieved, and thank you for your attention. We have public code available at the following address.